In this video, we're going to look at what makes something aromatic or anti-aromatic. Let's jump right in. Sometimes we have rings that are conjugated all the way around them, like benzene, that end up being extra stable. And when they're extra stable compared to something else with three double bonds that's not a ring, when it's extra stable compared to the open ring form of it, we say it's aromatic. Now, aromatic used to mean it has a certain bouquet or smell, but now we mean it's extra stable when we're talking about these conjugated rings. Now, not all conjugated rings are extra stable. Some of them that are conjugated all the way around, like cyclobutadiene, compared to its open form, it's extra unstable. So for some reason, this is extra unstable. It's not happy at all. So we say it's anti-aromatic. So I want to talk about what makes something aromatic extra stable and what makes something anti-aromatic extra unstable. Well, there are a couple of things. One, whenever we have a ring that's conjugated all the way around like benzene, you end up with something like this. Each carbon atom of the 6 carbon atoms in this ring, since it's double, single, all the way around it, every carbon atom has a p orbital on it. And if it's a flat ring like this, all of those p orbitals can overlap, and that wave-like nature of the electrons in the p orbitals can overlap, and they can start to make what we call molecular orbitals. So they can overlap and make different types of orbitals. The pi system bonds here, the pi bonds. So whenever you have a flat ring and these p orbitals can overlap, these electrons can be shared with each other. So that can make this either extra stable, like it is in this ring, or when they overlap like that, it can make it extra unstable. And the best way to understand that is to look at the molecular orbital diagrams for a couple of these compounds. So if you were to look at the molecular orbital diagram for benzene, you find it looks something like this. It has 6 molecular orbitals in the pi system. The bottom ones are all pi bonds that are bonds. And these top ones are all anti-bonding. And since there are 6 electrons in the pi system for these double bonds, they would fill up in these pi bonds right here. So we have 6 electrons that are in these more stable, lower energy pi bonds compared to just the p orbitals. But if I look at the molecular orbital diagram for this one, cyclobutadiene, since there are 4 p orbitals that overlap, because it's flat and they all overlap, we have 4 molecular orbitals. One would be bonding and one would be anti-bonding. And this middle line is called the non-bonding line. And since I have 4 pi electrons, 2 go into this pi bond, but 1 goes into here, and then we don't fill them up. They go into their own orbitals before we would have to double them up. So pi 2 and pi 3 each have 1 electron in the non-bonding orbital, sort of like a free radical. So these are very reactive. That makes this compound want to react right away, so it's not very happy or stable. It's very unstable. So because you have these unpaired electrons, we say this is anti-aromatic, very unhappy, wants to react right away. But since in benzene they're all paired up, it's very happy, nothing to go react, but it's very stable, we say it's aromatic. So whenever we have this situation when they're all paired up, it'll be aromatic. And when they're not paired up, it'll be anti-aromatic. Let's look at some other examples. So let's look at these ring systems. In each of these, they're conjugated all the way around. And every atom, every carbon atom has a p orbital. So these compounds are called annulenes. organic compounds that are conjugated all the way around and they're rings. So this one, if I were to look at its molecular orbital diagram, and for each of these, I want you to notice that I just take the shape, I turn it on its point. So if it's a triangle, I'll have 3 molecular orbitals, with the bottom one being a point. Same thing for this one. So we count the electrons. In this, there are 2 pi electrons. So there's 1 empty p orbital for that positive carbocation, and there's 1 electron for each of these p orbitals to make that double bond. So there are 2 electrons. I fill them in, 1, 2, and they're all paired up. This would be aromatic. This one, there's a p orbital with 2 electrons in it for the carbanion, and there's a p orbital here and here. So if it's flat, all 3 of those p orbitals can overlap. How many pi electrons do I have? Well, there's 2 for this pi bond, 1 for each of these p orbitals that come and join together, and there's 2 for this lone pair in that p orbital. So I fill them up, 1, 2, 3, 4. This would be anti-aromatic. This one we've seen previously. Notice now I have a square with the point on the bottom. That's called the polygon rule. I have 2 4 electrons, 1, 2, 3, 4. This would be anti-aromatic. This one, let's make my little pentagon shape with the point on the bottom. Conjugated all the way around. There's a p orbital here and here for that pi bond. Here and here for that pi bond. And there's an empty one right here for the carbocation. If it's flat, all 5 of those can overlap. So I have 2 4 pi electrons. So 1, 2, 3, 4. Unpaired electrons, anti-aromatic. This one would be a pentagon on its point. 2, 4, 6 electrons in this case. 2 for that bond, 2 for that bond, and 2 for that lone pair. This is a p orbital on every carbon atom that can overlap. So I have 1, 2, so 2, 4, 6, 3, 4, 5, 6. They're all paired up. This would be aromatic. We've seen this one already. 6-membered ring for benzene on its point. 2, 4, 6 pi electrons. 1, 2, 3, 4, 5, 6, all paired up, aromatic. This one's a heptagon. 1, 2, 3, 4, 5, 6, 7 on its point on the bottom. So I have double bond, so that's a p orbital and a p orbital overlapping to make that pi bond. This pi bond makes 2 p orbitals overlap. This one has 2 p orbitals overlapping. And this is a positive charge on that carbocation, so it's empty. So if it's flat, they can all overlap. And I have 2, 4, 6 electrons in the pi system. 1, 2, 3, 4, 5, 6. That would be aromatic. This one, the same 7-membered ring. But now let's count how many pi electrons. 2 for that pi bond, 2 for this one, 2 for that one, and 2 for that lone pair. So again, lone pairs or positive charges or double bonds all can give me that p orbital on an atom. So I have 2, 4, 6, 8. 1, 2, 3, 4, 5, 6, 7, 8. Anti-aromatic. So this one would be extra stable, extra unstable, extra unstable, extra unstable, extra stable, extra stable, extra stable, extra unstable. So here's what we have. We'll notice that whenever I have 2 electrons, I was aromatic. When I was 4 electrons, let's make that red. 4 electrons was a bad number for me. 4 electrons was a bad number for me. That was anti-aromatic. 4 electrons was a bad number for me. 6 electrons was good for me. 6 electrons was good for me. 6 electrons was good for me. 2, 4, 6, 8 electrons was bad for me. So we find that if you're a multiple of 4, 4, 8, 12, so 4 times some number, that's bad. That makes it anti-aromatic. if you're 2 or 6 or 10 or 14, the other even numbers, that gives you 4 times some integer plus 2. That makes you aromatic. So let's see what I mean here. If n is 0, 4 times 0 plus 2 is 2. If n is 1, 4 times 1 plus 2 would be 4 plus 2 is 6. If n is 2, you have 4 times 2 is 8 plus 2, that's 10. If n is 3, 4 times 3 is 12 plus 2 is 14. If n is 1, 4 times 1 is 4. If n is 2, 4 times 2 is 8. If n is 3, 4 times 3 is 12. So if you're 4n electrons, you're anti-aromatic. If you're 4n plus 2 electrons, you're aromatic. So the 4n plus 2 rule, or sometimes called Hückel's rule, is what we're looking for to make an aromatic compound. So you need 3 things. 1, you need a ring. That ring needs to be conjugated all the way around. So every atom has to have a p orbital. That could be something with a double bond. It could be something with a positive charge. It could be something with a lone pair of electrons. But you need something to cause it to be conjugated all the way around. A p orbital at every atom. And it also needs to be a flat ring, because all of those p orbitals need to overlap perfectly all the way around so they can overlap. If one of those p orbitals is kinked sideways, then they don't overlap any longer. So it needs to be a ring, conjugated all the way around, flat. If you have those things, then we look to see if it's 4n plus 2 for a number of pi electrons. That would make it aromatic. Or if it's 4n electrons, that would make it anti-aromatic. If you're missing any of these things, if it's not a ring, if it's not conjugated all the way around, if it's not flat, then you're neither of these things. Then you would be non-aromatic, nothing at all. But if you have all of these things, then you have to analyze it and see if you're aromatic or anti-aromatic. The best way to learn this is to practice a lot of problems. So let me give you a whole bunch and we'll just go through some, and pretty soon you'll pick up what to look for. All right, well, let's analyze these problems and see if we think they're aromatic, anti-aromatic, or non-aromatic. Okay, this one. First off, I need to look for the 3 things. Is it a ring? Yes. Is it conjugated all the way around? Yes. I have a p orbital here and here because of that double bond. I have a p orbital here and here because of that double bond. And I have a p orbital here and here because of that double bond. So then, if it's a flat ring that's conjugated all the way around, I've got all 3 things. I count 2, 4, 6 electrons. That is equal to 4 times 1 plus 2. So that's 4n plus 2. This is aromatic. This one, is it a ring? Yes. Is it conjugated all the way around? It is. There's that pi bond. There's that pi bond. And here we have a lone pair on that nitrogen. So these 2 electrons can be in that p orbital of the nitrogen. So I have 2, 4, 6 electrons. That's 4 times 1 plus 2, 4n plus 2. So this is also aromatic. This one, do I have all 3 things? Is it a ring? No, it's not. So this one, I never even get to count to 4n or 4n plus 2. This is non-aromatic. It's not aromatic. It's not anti-aromatic. It's just nothing. So I didn't have a ring. How about this one? Is it a ring? Yes. Is it conjugated all the way around and flat so those p orbitals can overlap? Well, let's see. There's a p orbital here and here because of that double bond, that pi bond. There's one here and here because of that pi bond. There's one here because of that lone pair. But this one, this CH2 down here, there's no p orbital here, so I am not conjugated all the way around the ring because of this. So this is non-aromatic. I never even get to count to 4n plus 2. This one, is it a ring? Yes. Is it conjugated all the way around? P orbital because of that pi bond. Here's a pi bond, so p orbital and p orbital. And I have a p orbital here on the oxygen because there's a lone pair. There's actually 2 lone pairs. I'm only going to count one of those lone pairs in that p orbital because you can only put 2 electrons in a p orbital in any orbital. So that means when I count this, there are 2 for this double bond, that pi bond, 2 for this pi bond, and 2 for one of these lone pairs of electrons. So 6 electrons. That's 4n plus 2. So this is aromatic. This one, is it a ring? Yes. And in fact, it's 2 rings fused together. So I'm going to count this entire ring when I count this one. Is it conjugated all the way around? Well, yeah, it looks like it because there's a double bond here. So a pi bond with 2 p orbitals. There's 2 because of that pi bond. There's 2 here because of that pi bond. And there's 2 here because of that pi bond. So all of these, if this is flat, they can all overlap all the way around. So now that means I have to count, since it's a ring that's flat, that's conjugated all the way around, I have to add up all of my electrons to see if I'm 4n or 4n plus 2. So I'm just looking at the pi electrons. I have 2, 4, 6, 8 for those 4 double bonds. So 8 electrons, that's 4 times a number, 4 times 2. So this would be anti-aromatic. So that means I think this would be hard to make. Not very stable, very reactive kind of compound. This one, let's look at my 3 things. Is it a ring? Nope, I'm not even a ring. I am conjugated all the way down it, but it's not a ring, so this is non-aromatic. It's not extra stable or extra unstable. How about this one? Is it a ring? Yes, it's a ring system. Is it conjugated all the way around? Well, let's look. Here's a pi bond, so there's 2. 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 This CH2 right here is not a p orbital. So this is a problem for me. I'm not conjugated all the way around. So that means all the p orbitals can overlap all the way around the ring, so I am non-aromatic. It's not extra stable or unstable. Well, let's look at this one. 3 rings kind of fused together, so I can count this one big ring system. Let's see if it's conjugated all the way around. P orbital with that double bond, that pi bond. Here's a pi bond. Here's a pi bond, so those 2 p orbitals. Here's one, and here's one. So on this carbon, though, I do have a lone pair, so I can put those 2 electrons in a p orbital. So it looks like I'm conjugated all the way around. So if this is flat, how many electrons are in the pi system? 2, 4, 6, 8, 10, 12, 14, if I count those 2, which I should count. So 14. So that's 4 times n, that would be 8, 12, 16. Nope, so it must be 4n plus 2. So if this is a 3, yep. If that's a 3, I have 12 plus 2, that's 14. So since I'm 4n plus 2, I'm a ring that's conjugated all the way around flat. This would be aromatic. So that's a pretty stable ring for some reason. All right, how about this final one? Is it a ring all the way around? Yes. Is it conjugated? Yes. If it's flat, do I have, well, it's conjugated all the way around. Let's double check that. Pi bond. There's a pi bond, here's a pi bond, here's a pi bond, and here's a pi bond. Yes, I am conjugated all the way around. Every atom has a p orbital. So if it's flat, how many electrons do I have? 2, 4, 6, 8, 10. That would be 4n plus 2. If n is a 2, that'd be 4 times 2 is 8, plus 2 is 10. So 4n plus 2 is good. That makes this aromatic. I hope that makes sense. That's the basic idea behind aromatic and anti-aromatic compounds. Please subscribe to the channel so I can continue to help you with your organic chemistry.